Hello guys, welcome back to my channel Gamma Digamma again. I apologize for being extremely infrequent. I think it's been the longest break I've ever taken from YouTube. But there was so much going on in my life and in my semester at Cornell. So I'm in Vienna now for some summer work, which I may talk about in the future videos on my channel. I'm making a video at an awkward time relatively because I was thinking if I make a video again, which I was fully intending to, because as I said, I'm never really gone. I'm there even if it takes me some time to come back up again. It would be on a series, like a lecture series, a topic series, because there's some really beautiful topics in mathematical physics that I wanted to share with the world. But I'm making a video today because there was this new proof of the Pythagoras theorem that was discovered by two high school girls from the US. And when I saw the proof, I said, well, this is something else. This is really cool because the traditional proof that is taught uses similarity of triangles. It's complicated. The construction is complicated. Construction was, the one of the only thing that sort of made geometry more tedious and annoying for me when I was in high school. Well, I never would have imagined I'm going to make a video on something like that back then, but here I am. So, like I say, let's get started. Okay, so the first thing is the construction, but the construction is not that bad. And I'll explain why. So, since it's Pythagoras theorem, I'm going to present what people have been presenting on other YouTube channels, because I think these girls, they presented it in a talk somewhere. They didn't really formalize it into a paper, which they are going to, I hope. So full credit to them. I'm not trying to take credit from anyone, and full credit to the YouTubers who've done it before me and whose sort of videos I used as a reference to construct these notes. So we have this one triangle, the one I drew on the right side. We sort of mirror that with respect to this side, that this vertical side that I'm going to call small b. The angles will be capital letters. So this side, let's call that small a. The angle opposite to that side, I'll call capital A. Capital A here again, and then this is capital B. Caps B. Now this suggestive notation will play a useful role later. Now the construction isn't done here, so now what I have to do, and I will try to keep changing the color so that I don't lose everyone. And again, if you have any doubts about any of the steps, please feel free to ask me in the comment section. I'm going to extend the hypotenuse, which I should have called C, in a suggestive, sort of pre-Pythagoras theorem setup. So I extend the hypotenuse down. And what I do is I take sort of the line that's perpendicular to the other hypotenuse, line that's perpendicular to this hypotenuse, which will be line that's going like that. So let me try to sketch that. It will go something like that. And both of these lines will intersect somewhere at some point. Note that this is a right angle because I said it's perpendicular just by construction. So which means if this angle here is B, the angle here has to be capital A, because A plus B are 90 degrees from just this top triangle here. I'm going to assume people have, sort of basic exposure to high school geometry theorems, like, some of the angles in a triangle is 180 degrees and all that stuff. Now what I'm going to do is, well, the last step of the construction is to sort of chop this yellow extension of the original triangles into these infinite sort of steps. Yes, these steps. Now the main thing is to keep our notation straightforward. So what I mean by that is, how are we going to label each side of these infinite steps? Well, if we call the vertical side B, we can call this vertical side B prime. This is A prime, this is a right angle. And this is a right angle, which means this is A, because the sum of all these have to be 180. So A plus B make 90, and we have a 90 here, so that's 180. So that's perfect. And since that's A, this has to be B here. And then C prime in a suggestive notation. And now after that, we have a C double prime. And the same sort of story. This is A, that's B. There's a B double prime. That's the B double prime. That's the A double prime. And so on. So, you see this pattern continues. Now, another thing I should do is mark this other side, which will also play an important role. So this I shall call X prime. Maybe I should have used small x, because capital letters for angles. I'm trying to be as consistent as possible, because there's lots of things going on here. Okay, if you call that X prime, then this thing should be suggestively X double prime, and so on, and like that's X triple prime, for example. Anyways, that's the construction. Yeah, so what I've done here is I've just marked the triangles that are similar to each other and that we should consider identically. So what I mean by similar is that the angles are all the same, so they're just rescalings of one another. And I've marked the similar ones in blue that we can consider identically, and the ones in red. What's important in this proof is, and what it relies on mainly, is the law of sines, and the fact that the law of sines does not depend on the Pythagoras theorem in any way, and therefore our proof is not circular. So I will just write the law of sines for the original triangles, the triangles in white, which goes as A over sine A equals B over sine B equals C over sine of the angle that's opposite to the side C, which is the 90 degree, which is just C. Now you see why there was this suggestive notation that B is the angle opposite to the side B, and then it naturally fits nicely into the law of sines as we know it. I will prove the law of sines in a separate video and show you that it's really independent of even right triangles. It just depends on, it just needs the angles of a triangle and their corresponding sides opposite the angles. Anyways, I've marked similarity because we're going to use proportions of the form, like in the white triangle that I've marked with blue. B is to A is to C. We shall get B prime is to A prime is to C prime for the corresponding green triangle that I've marked with the blue dot, and so on. Now we start first by looking at this hybrid colored triangle. What I mean by that is the one that has the side 2A, the B prime side in green, and the hypotenuse as this side in yellow. What I'm going to do is I'm going to apply the law of sines. So 2A over sine B, because that's the side opposite the angle opposite to the side 2a is b, equals b prime over sine a. Pause the video if you've not used the law of sines and are just seeing the formula that I wrote down for the first time. This gives us, with the algebra, 2a sine a over sine b. Now sine a, if we look at the original triangle, is opposite upon hypotenuse, which is a over c, and sine b is b over c by definition. So we just get 2a squared over b. That's for b prime. We can find c prime in a similar way by applying law of sines. Either on this green triangle we can apply law of sines, or we can just use the proportions trick here by just multiplying by the right scaling factor. For the initial ones, what I've done is I've applied the law of sines. So c prime will just be b prime over sine of b, and we have 2a sine a over sine squared b, which we can simplify with all the algebra, 2a squared over b squared times c. Fair enough. We also need to find the value of this x prime and x double prime and x for later uses. You'll see why. It all fits together nicely. So x prime is 2a over b times c. You can find that by doing law of sines on this hybrid triangle that we started out with first. We can find x prime by that, or you can use proportions, since you know what b prime and 2a, and you know two of the sides. Okay, now x double prime can also be found because we know let's see, we can find a prime actually. Let's actually find a prime first, because we need a prime. So we're now doing this triangle. We need a prime to sort of use the either law of sines or the proportion to find x double prime. So a prime is, I'm skipping lots of steps. Pause the video and do them for yourself if you do not agree. 2a cubed over b squared, and then x double prime just becomes 2a cubed over b cubed times c. Fair enough. Now we can use this value of a prime, 2a cubed over b squared, to find b double prime and x double prime. Well, we found x double prime, but now we can find b double prime, which is this side, so that we can find the value of c double prime, because then we will be in the other triangle. Notice the roles of in this proportion. B prime is the side that is opposite to angle B. Notice when we go to the red dots triangle, the red dotted triangles, the role of A and B is flipped, because A prime is sort of like the B element of the blue triangle, because A prime will now be opposite to the angle B. So just be careful when you're applying the proportion. Know what is proportional to each other. So that's why these angles are good reference points of which side is actually acting as the sort of the functional A or the functional B, or whatever you want to call them. Yeah, choosing colors is always confusing here. Okay, so we have a proportion set up for the red triangle that I just pointed out, and we can find b double prime based on this proportion, or the law of sines, whichever you prefer. We know this is proportional to the first one we used, b is to a is to c. And just note how the roles have changed, because we're considering the red dotted triangle. So the what looks like or has the b is actually in the place of the a. B double prime is in the place of a. Just take note of that. That's all. So since you know this, you can move on to the next blue, the blue triangle in there, to find the value of c double prime. So the proportion will be set up like this now. So now we will have 2a to the fourth over b cubed, our b double prime value, with a double prime and c double prime. Since it's a blue triangle, so the BAC quarter is sort of maintained. So c double prime becomes 2a to the fourth over b to the fourth times c. Well, that's good, because we know we have a sort of a sequence which will only repeat, and you can check that it repeats using the proportion that we set up. So notice c prime was 2a squared over b squared times c. C double prime is 2a to the fourth over b to the fourth times c. This surprisingly looks like a geometric series, which is good because we have to sum all of them. That's the c stuff going on. The x is also doing this geometric series. We have a 2a over b times c, and then we have a 2a cubed over b cubed times c. So let's add these things together. So let's add the x's first. Maybe let's call that capital X, and I shall use a different color. Now white can return. So when we add them together, so the first term is the x prime term, 2a over b times c plus 2a cubed over b cubed times c, and then so on. That's the pattern. So using the formula of the geometric series, we have the first term, 2a over b times c, over the common 1 minus the common ratio. The common ratio here is a squared over b squared. You can just see by dividing consecutive terms. And for the c, maybe I should have put a tilde. I'm going to put tilde at the c. We're summing from c and then c prime, c double prime, so on. So you see the pattern only starts from the c prime. The c is sort of like a standalone value. So c plus the c prime, which is 2a squared over, is that b squared? Yeah, b squared c, and then the c double prime value, 2a to the fourth over b to the fourth times c, and then the pattern continues in a geometric progression. So it's c plus the infinite geometric series. So it's going to be the first term, which is 2a squared over b squared times c over the common ratio, which is 1 minus a squared over b squared again. We can simplify this a little bit more. So b squared c minus a squared c plus 2a squared c over b squared minus a squared. Okay, and then we get by some algebra, we get this relationship. Now let's divide these guys out. So let's x tilde over c tilde. We get, let's see, 2ab over a squared plus b squared, I believe, because some terms will cancel out. Yeah, you can check this out if you don't believe me. Now this x big tilde over c big tilde. Now let me mark what those things are. So x tilde is this entire length on that side, and c tilde is like this entire length. So if you sort of divide them out, that's just going to be the sine of this angle, sine of 2a. If you look at the big triangle now, it's going to be the sine of 2a because it's opposite over the hypotenuse, because this is the right angle, the hypotenuse has to be the c tilde. So that is really the sine of 2a, just by definition of this triangle. It's this entire angle, not a, it's 2a. Okay, so let's write that down. We know this is sine of 2a. Can we use some law of sines on the sine of 2a, because we really need to simplify it. And we can't really assume the double angle formula here. let's just say it's not proven. So sine 2a according to this triangle, and that's the beauty of the law of sines, is it's not dependent on a right triangle. Let's consider this entire like triangle, both of those merged together, which is not a right triangle, but it works because sine 2a, you can write that down here. According so in the big triangle is sine 2a, or let's say it's this side, which is 2a, the entire side, over sine 2a equals b. It's getting sort of hidden behind b over sine of b. And then we can solve for sine 2a. Sine 2a then becomes 2a over b sine b. Sine b is b over c. Let's hang on. Let me just check my steps again. So we have sine 2a. It will be in the denominator. So 2a over sine a. And then I think I made a mistake. It's going to be b over the side that's opposite to it. So this side is not really in this triangle. It's not part of the triangle. So the side opposite to b for the law of sines will now be c. Yeah, that was my mistake. I apologize. So it's going to be c over sine of b. And now sine of 2a you can solve, becomes 2a sine b. So 2a over c times sine b. Sine b is just b. Sine b is just b over c. So it's 2ab over c squared. We can just plug that in here in this equality. And do you see it? The Pythagoras theorem. Because these terms drop and we get in the denominator a squared plus b squared is c squared. There we go. I never thought I would really prove the Pythagoras theorem on my channel because that's really not the focus of my channel, but there you go. I think this is probably the best proof of the Pythagoras theorem I've ever seen. So really kudos to these really smart girls for like figuring this out. I am guessing you can do this with the law of cosines, but it gets more convoluted, and probably the algebra is ugly because there's squares of terms involved in that case. The law of sines is beautiful. There's also, I believe, a law of tangents, but again, tangents are complicated to work with. Sines and cosines are the very first trigonometric functions you encounter anyways, and everything else is just made up of them. Yeah, I shall prove the law of sines in a future video, maybe with like vectors or some basic geometry, some similarity construction stuff. But thanks for watching, guys. I apologize for the delay, but I'm still here. I'm thinking of new ways of putting forth out to the community. So please let me know what you think. Peace out. Thanks for watching.